So you might think, like, how does a mathematician get involved in this? Let me have you close your laptops for now so that you soak this up. So actually, I was at West Point in 96 to 98, as similar to Dr. Groves. And I, new time, we never ate, played basketball. I was really active. I was active at Georgia Tech. I think I took my classes in the morning, played about 3 or 4 hours of basketball, pick up games, and then came back and did my homework. And then I maybe taught a class somewhere in the morning too. So like I left West Point, got married. Like it's harder and harder to actually go play basketball for hours on end. And so I gained so much weight. And then we also had a diet change because my husband's family is vegetarian, so we had vegetarian food. If you change your diet like that, you feel hungry all the time. So I gained about, I think, it was about 175 pounds towards the end of all this. And I did lose the weight, but I became kind of fascinated between like how people eat, what makes them gain or lose weight, what actually makes things. Why do some people eat and they don't seem to, nothing seems to happen to them? It just melts right off of them. And so I had these questions in my head. I got involved with a few other investigators, and one of the ones that I got involved with was Corby Martin, who's a psychologist, and he's always interested in the psychology questions. And so there was these people that used to, like, there's a famous psychologist named Kisselov. He's probably in his 80s now. He's in New York, and he's done these really famous studies where, you have, a wall and there's a straw and someone's sucking a shake from the other side, but they can't see the shake. And he tells them to drink it until they can't drink it anymore. So you look at satiation is what we call it. You feel satiety. And he wanted to see like how different people, maybe normal lean people versus people with obesity, how they react to these things. And Kisselov developed this machine, and it's called the Universal Eating Monitor. And it's got a scale, and you put your food on the scale, and it starts to calculate the grams that are coming off the plate. And then what you'll get from the device itself, there's different ways you can like plot this, but the way he had it plot was the cumulative grams, like a cumulative distribution curve, something like that, as the cumulative grams that have come off the plate. And what you start to notice is, what we noticed is that sometimes it looks like somebody's curve is not really a curve. The cumulative stuff is like linear. And sometimes people eat and they start to slow down towards the end of whatever they're told to eat. So over time, this is, they had calculus, and so they had all the courses that you can imagine. They're good scientists. They're not like your, scientist that's at, Montana's community college. It's like a big college. He's at Columbia. And so what he did is he fit this, he says sometimes it's a line, so we're going to fit that with mx plus b, and sometimes it's a quadratic, so we're going to use ax squared plus bx plus c. Now, I think this is probably the second person with real quantitative skills that came into the field. And then another friend of mine, she was a Harvard physicist, she came into the field, and we looked at this and said, whoa, this actually gives you nonsensical solutions. Because if you fit something with a quadratic, it's going to rise up, hit its maximum, and then eventually as the person's growing up, like what's going on here? Like so it doesn't make sense long term. And really, you shouldn't have two different models. That's kind of bad. It doesn't explain reality. Why should someone get this curve over this curve? Should be one model that explains all of this. And so we felt that that model would be the Verhulst model, the same model that you guys studied with for the homework with Dr. Groves. Kind of, not quite, but almost. What was interesting about that model is that it had 3 different parameters. The Verhulst model has 2. It's the R and the K, but we think there's a third one, and that's your initial rate of how fast you take up food. Because at time equals 0, it's not 0. There's a number of experiments that I read to go over this, and there's a history of how all this works, why you eat fast and why you eat slow, when you feel full and when you don't. There's actually hormones that are generated, and the first one's called ghrelin. So if you withhold food, I don't know if they've done this in a person, it's probably not legal to do this in a person, but they've definitely done it in mouse studies where they withhold food and then let them eat. They eat faster. The longer you withhold food, the faster you eat. So they were discovering that there must be something that's released in the body that makes this mouse hungry. And we know now that's a hormone called ghrelin. So when you're starting to feel hungry, it's ghrelin that's starting to go. Then there's something that makes someone stop. Otherwise, they just keep eating. So they experimented on mice to kind of figure out, like, why does a mouse stop eating? They're almost cruel. They're very cruel studies, actually. If you like mice, you kind of like, oh gosh, this is terrible. But over time, they developed this like idea that there's these hormones that come out and get you to stop eating, and that's a hormone called CCK. It inhibits your intake. So it's really interesting watching people, because you'll see people like, and now I just watch people all the time. So when they're eating, they'll eat really fast at the beginning, most people, and then over time, I don't know how the mess hall goes, because that's really, like, you will have such a short time. But over time, they'll start to talk more and then slow down, and you'll actually see it. So I'm going to ruin your mess hall experience today. When you watch people eat and see that they eat differently. And so what we advocated for is one model. So the name of this paper is called a universal model, to describe eating rates and cumulative intake curves. These are the cumulative intake curves here. So this is the model. We felt like everybody has like what they have as their carrying capacity. It might be different for me and you, but we have our carrying capacity. And we also felt like when E is 0, the dE dt is not going to be 0. It's not an equilibrium point, because the second you hit the plate, you're going to start scooping things up. You're hungry. And so your theta here is going to be your initial rate of how fast you start eating. So those are two variables. And the R is, of course, your rate of how you're consuming grams per minute if there were no carrying capacity to slow you down. So that's what I did. Instead of R E of t, we needed to bound this away from 0. This satisfies the quasi-positivity theorem that I just told you. So I know that my solutions have to be non-negative. So I had to check all that. And we actually write in prose in this article about why one model is needed. It's called first principles modeling. And we explained how all this matches up with the literature, why it should make sense, why the assumptions make sense, and so forth. It's being recorded, but we think Kisselhoff was our reviewer, and so he wasn't going to let it go. So we had to clearly explain, we realized we had to clearly explain what was going on, not necessarily for Kisselhoff, but maybe the editor, to say, this paper's going through, regardless of what the reviews are. And Colonel Painter came to my office and saw this on the thing, and I said, they're asking me for all these things. And he's like, I can do that. And so that's how he became my first co-author here at West Point. You can solve this with separation of variables, just like the Verhulst population model. If you did the homework, it's partial fraction decomposition. It's nasty. And the real idea behind the physiology is there's two stages of eating. There's a stimulation phase. You're going to see that in the mess hall today. Some folks are going to come in and eat really fast. And then there's a phase right after that. I didn't draw it. There's a satiation phase, and it goes right like this. I should have drawn it. It'll go like this. Satiation phase. What's this point right here? Inflection point. That's right. I get asked that a lot. What is that inflection point? So I can actually calculate it. Once I have your curve, I can calculate when that's going to happen. Oh, I do have that, a satiation phase. Okay, so I'm actually just going to have you play around with the model for the rest of the class period. I gave you the code with Mathematica, so it should be easy just to run it. And just fool around with those parameters, and then fill in the tables where I have, like, just that's the whole point of differential equations. Have a good model to start out with. Make sure it makes sense. Make sure your solutions exist. Make sure that they're non-negative. When the values are 0, it should still make sense. Something shouldn't be disappearing. Shouldn't have loss of lean mass when there is no lean mass. Stuff like that. You have to kind of make sure that things make sense. And then you try to understand reality from moving around these parameters. Like, what if someone sits down and they eat furiously fast right away? That's R. So that's the tweak of R. What if their initial rate is really fast? What if their carrying capacity is really high? So Corbett Martin had done a study with the Universal Eating Monitor with people who are lean and people who had obesity. The people with obesity ate longer. That was like the takeaway I had from it. And because he didn't see anything else. And I said, okay, if they eat longer, they're more likely to like have a higher carrying capacity. So it seems like Emax was really important for people with obesity. And they indeed know that CCK, ghrelin is higher in people with obesity, and then CCK comes out at a later point for people with obesity. So they are different. All right, go for it.